Welcome back, students. Let's begin Chapter 3, Descriptive Analysis and Presentation of Bivariate Data. In Chapter 2, we did a lot of descriptive analyses, but they are all about a single variate data. For example, we studied a score distribution of a certain class or a certain exam, and we presented those data with stem and leaf chart, histogram, ORGIF, box whisker chart, and so on and so forth, graphically, and numerically, mean, median, quartiles, standard deviation, we did those kind of things. All those are good examples of descriptive analysis, but all those were for a single variable, exam score and nothing else. Now, what if we have two exam scores per student, like midterm and final? In that case, we can do all those descriptive analysis for midterm exam, do the same thing for the final exam, and then we can consider the relation, which we call correlation. Basically, that's what we're going to do in Chapter 3. This chapter is structured as follows. First, we are going to talk about the meaning of bivariate data and look at some examples. And here we're going to go over some graphical way to present those, like contingency table, side-by-side chart, like side-by-side histogram, side-by-side box whisker chart, side-by-side everything, and most importantly, scatter plot. And in the next section, 3.2, we're going to talk about a quantitative, numerical way to represent the correlation, which we call correlation coefficient, and we talk about how to calculate it, what it means, and things like that. Now, how to use that correlation coefficient and do some prediction, that's going to be the topic of 3.3. Here, you're going to have a glimpse of what's to come in the latter part of this course, inferential statistics. Needless to say, 3.3 is going to be the most important topic here. Nonetheless, let's begin with 3.1. Now, what is bivariate data? Here's a summary. The values of two different variables that are obtained from the same population element. For example, in that motivation example, I talked about midterm and final exam scores. Now, it is very important that those exam scores are coming from a same student. For example, if I get a data set by midterm score from one student, final exam score from another student, and they're all jumbled up, that's not going to be a bivariate data that you can really work on. Each exam score has to be paired accordingly. For one student, we have midterm and final, like x comma y, kind of like that. But that's going to be a little bit harder example because both are going to be quantitative variable. So let's begin with something easier. Two qualitative variables put together. Here's a table 3.1, and this is a kind of sample study for a hypothetical situation. We have 30 students with some names. Names are not that important. We have first variable, gender, male or female, and the second variable, major, liberal arts, business administration, and technology. They are both nominal qualitative variables. So what we can do mathematically is rather limited except for counting. That's basically what we are going to do. Now let's consider this in a little bit more detail. For that purpose, let's open up my notebook here. Here is the same table here. And let's do some counting. Let's count the number of male liberal art majors, female liberal art majors, male business majors, female business majors, and so on and so forth. And put those in a table. And that kind of table is called contingency table. Actually, one example of a contingency table, to be a little bit more precise. There are other things too, based upon perspectives. Now, what kind of mathematics do we do? By those counting themselves, well, there isn't much we can do. And also, they are not that important. So what do? We take ratio. Consequently, we end up with a second contingency table. This is going to be a little bit more interesting, more useful. For example, if you want to predict or estimate the proportion of, say, liberal art majors, female liberal art majors in this entire college, for example, then the best point estimate is going to be 20%. Why? Because we have 6 female liberal art majors in this sample out of total 30 students. So 6 divided by 30, 1/5, so that's going to be 20%. So the best point prediction for this entire college is 20%. 20% of this entire college will be female liberal art majors, give or take, of course. For example, if you're going to concentrate upon, say, male technology major, you can do the same thing. 7 male technology major out of total 30. So 7 divided by 30, what do you get? We get 23%. This kind of thing is an example of a contingency table. Oh, by the way, here is a bar graph that goes with it. For example, male liberal art majors, 17%, and then look at the height of the first box. It goes about 17%. And then next, female liberal art majors, 20%, and the second bar just go up to 20%, and so on and so forth. Is that all? Actually, no. Actually, we can do far more than that. We can change the perspectives, and then we can consider conditional proportion or relative proportion. I prefer the term conditional proportion a little bit better because it has intimate relation with conditional probability, which will be a main topic for the next chapter. What do you mean by that? We can put a condition and then consider proportion after that. What kind of condition? One way to do that is to restrict the gender. Let's see, among all male students here, what percentage of those male students are technology majors, for example? Well, in that case, the 12 female students here in this sample contribute nothing. So throw those away, and then the total number of students that you have to consider will be 18. 18 men in this sample. Consequently, what you have to do is 7 divided by 18, which is about 39%. You can do the same thing for other majors, for other genders. For example, what is the proportion of business majors out of all female students? You don't have to care anything at all about 18 male students, so the total is now 12 female students. Out of those 12, 4 are business majors, so 4 over 12, 1/3, about 33% of the students, about 33% of the female students are business majors. Those kind of things are called conditional proportions or relative proportions. I prefer the term conditional proportions. By the way, here is those conditional percentages based upon those conditions, let's say conditional proportions based on major is set, but the condition is the gender and the percentages of major. Percentage of major given the condition of gender or something like that. My English is not my first language, so I sometimes struggle in creating those kind of phrases. Anyway, this is another contingency table that reveals another side of this same sample statistics. What if we change our condition? Instead of putting our conditions into gender, we just put those into major first. Out of 11 liberal art majors, 5 of them are male. So let's forget about the other 19 students and just look at 11 liberal art majors. So what do we get? 5 divided by 11, which is about 45%. That's how we get conditional proportion. This time the condition is the major and a proportion of the gender. What if you want to find out the conditional proportion for female students out of all technology majors in this college? Well, total is 9 in this sample, and 2 of them are female, so 2 9s, we have about 22%. By the way, here is the box chart, a bar graph that goes with this second or third contingency table. This is a fourth contingency table. And I don't like this this labeling here. Our textbook author called percentage based on major for both of these charts. And this one, percentages based on major, as if they are the same, but they are not the same. The first one should have been labeled as percentage based on gender. I think. Okay, so much for the simplest example where we have 2 qualitative variables. And let's go over to the next example that we have to work on at least 1 quantitative variable. Here's an example, and we have 2 sections, section A and section B. Section A is blue, section B is green, and each section we have 2 exams, midterm, final, and we have all these scores. And this data set is just hypothetical. Okay, we can do a lot of these depending upon viewpoint. For example, we can consider histograms of exam 1 for section A, the blue one, and then histogram for exam 1, it has to be the same exam 1, for section B, green one, and then compare them side by side. Or you can do those things with the averages. You can do various things here. And well, here's one example. Side by side box whiskers chart, for example. So the blue one is section A, box whisker chart. So we have first quartile, minimum, first quartile, median, third quartile, and maximum. And then for green, which is section B, we have minimum, the lowest, and then first quartile, median, third quartile, and then finally maximum. You can do the same thing for the second exam score. As you can see, we have a little bit more concentration for blue, section A, and then in section B, scores are a little bit more spread out. Here's an example of side-by-side histogram. Class interval size is given as 10, and then blue is section A, green is section B. You can do various things. Now, the third way, probably the most important, is called scatter plot. In this case, both first and the second variables have to be quantitative, like here in this case, exam 1 versus exam 2, or homework 1 versus homework 2. Again, this is not real scores. These are hypothetical scores. And then here is an example of a scatter plot. Exam score. X-axis is first exam score. Y-axis is a second exam score. Each dot represents a student. For example, in the top, this right-hand side dot where my mouse is, this student scored about 90 in the first exam and then barely over 70 in the second exam. This kind of thing is called the scatter plot or scatter diagram. We have a similar picture down here. which compare the first homework and the second homework.